In the previous article, we discussed about the force on a charged particle when it is subjected to electric field and magnetic field. We find there when a charged particle is placed in magnetic field, it experiences a force and the formula was F is equal to QVP sine theta. Since conductor is made up of large number of such particles, so here in this lecture we are going to find out the force on a current carrying conductor placed in a uniform magnetic field. For that, let us consider a current carrying conductor is placed in the magnetic field. As in previous article, there was the magnetic field in z direction, the magnetic field was B. Here we are also taking the same type of considerations. So let's start. So first of all, let's make the coordinate system like this. Say this is x-axis, this is y-axis, and this is the third one, that is z-axis. This is a current carrying conductor of length L is placed in the magnetic field. This is the direction of magnetic field, that is along y-axis, and this makes an angle theta with the direction of magnetic field. This is the direction of current in this conductor. Then the electrons will move opposite to the conventional direction of current, and that is in this direction. This is the direction of flow of electron in this conductor. This end of the conductor is A and this end is B. As current flows from A to B in this conductor, then electrons will drift with drift velocity Vd from B to A. As electrons are there, and electron is a charged particle, and in previous article we discussed that when a charged particle is subjected to magnetic field, or we can say moving charged particle is subjected to magnetic field, it experiences a force. So every electron in this conductor, which we have considered here, also experience a force, and that force can be expressed as, that is F. I'm writing with a small f because this is the force on a single electron. That is equal to minus E. Why minus E? E is the charge, that is Q, and negative sign, since it have negative charge, that's why I'm using negative sign here. And V cross B, we know that, and Vd is the drift velocity here, and B is the magnetic field. Say this is equation number 1. Now if A is area of cross section of this conductor and N is the number of electrons per unit volume in this conductor, and L is the length of the conductor, then total number of electrons in this conductor, if are N, that can be find out simply, that is A into L, that is volume, and N is the number of electrons per unit volume. The total volume is A into L, and N is the number of electrons per unit volume. So the total number of electron in this are N. So this is the total number of electrons which are in this conductor. Now we know that force on one electron is given by this, and since there are total number of electrons N, so the total force, that is F, that will be equal to N into F. We can write like this. So we can write here, that is the magnitude of force, that this F, that will be equal to N. N is A L N, and value of small f is E V D B sine theta. I'm converting into sine, and negative sign is there, so this will be there. Since negative sign represents just the direction, so I leave this negative sign here. Then we can write that this F, this will be equal to N E A V D L B sine theta. And I think this part we have completed earlier, and this is known as current. So we can write this force I L B sine theta as we have done earlier, that is NEAVD, that is equal to current. We discussed this in second unit. In vector form, we can write that this F vector, that is equal to I L vector cross B vector. So this is the force in vector form. And vector have direction. Then how we find the direction? That can be found with the help of right hand curl rule. According to right hand curl rule, the direction of a force will be perpendicular to both L and B. That is the length of the conductor, that is in the direction in which current is flowing. We cross our fingers from the direction of this conductor, that is the direction of current, to the direction of magnetic field. Then we find that the direction of force is perpendicular to both x-axis and y-axis, that is along z-axis, and directly outward. This direction can also be found out with the help of Fleming's left hand rule. If you don't know about the Fleming's left hand rule, then you can watch that. The link is coming on upper right corner in eyeball. By clicking that, you can watch that. Now let us discuss some of the special cases related to this. Special cases. The first one, when theta is equal to 0. That means the conductor is in the direction of magnetic field, and we know that when theta is equal to 0, then sine 0 is equal to 0, and again the force will be 0. That means the conductor will experience no force. The second point, when theta is 90 degree, and we know that sine 90 is equal to 1, which is its maximum value. So maximum force will act when the conductor is perpendicular to the magnetic field, and that will be equal to ILB. So the maximum force will act on the conductor when it is perpendicular to the magnetic field. Say that is along x-axis or z-axis if the magnetic field is along y-axis. Now let's try to find out what is the work done by a Lorentz force. As we know that work is a force into displacement, that is the dot product of these two, that F S cos theta. And up to now we know that Lorentz force and motion are perpendicular to each other. That's why angle between them is 90 degree. And thus when theta is equal to 90 degree, then F S cos theta, or we can say cos 90, and cos 90 is equal to 0. So this will be 0. So work done by a Lorentz force is 0. So this was a simple and straight article. In this way, we can find out the force on a current carrying conductor when it is placed in magnetic field. Now, what happens if two conductors are there and those are placed in magnetic field? In the next article, we will discuss about them. And if you want regular notifications of videos which are uploaded to this channel, then click on a subscribe button and also press the notification icon so that you get all the videos, all the information or all the lectures which are updated on this channel. Also, you can join BHAUTIQ Telegram group where all the notes, PDFs will be shared. So this was all about for this lecture. Thank you very much.